Okay, good afternoon, everyone. We're going to start a new unit today, new topic on classification. And we'll actually spend quite a while on classification as a focus. So in this case, the motivating example is diagnosing breast cancer. And the idea is that what they do is they will take tissue samples and someone will stain them and look at them in a microscope. And then they'll record various values for different things they see. For example, things about uniformity of cell size, uniformity of cell shape, clump thickness, and so on. And so there's a data set where there's 683 samples, 9 features here on the right. And then the target in this case will be whether there's cancer or not, whether it's malignant or benign. And then to get that ground truth, they did a biopsy and they got a definitive diagnosis. And the question is, can you predict that diagnosis from aspects of the cells that you can see in a microscope? So that's the data set. And what you see here, there's a couple interesting things about this. So first, something that's a little bit strange is that all these features here, okay, the first feature, the ID number of the sample is obviously not relevant, right? But when you look at all these other features, you see that they are integers from 1 through 10. So do we want to think about these as categorical or as ordinal? What do you think? How many people think that we should do like one hot coding and think of them as categorical? Okay, no, we don't want to do that, because even though they're discrete, all these things are ordinal, like thickness, 1, 2, 3, or so on. Those are ordered, right? 1 is less than 2 is less than 3. So just because they're discrete does not mean you want to treat them as categorical. These are definitely all ordinal. On the other hand, the class here, this is different than what we've seen so far. In this case, the class takes on one of two values. In this data set, it's either 0 for benign or 4 for malignant. So we've never seen a discrete class variable until now. And that's what actually makes classification different from regression as we've seen it so far. Okay, so let's take a look. Let's try to visualize this data. So there's sort of two things that are challenging about visualizing it. So if you just try to use a scatter plot, which is what we're used to doing, you would find that all the samples, all the features land on top of each other because they're discrete values, 1 through 10. So here in this plot, we're just extracting 2 of the features, marg and size unif, and we're trying to see what happens as a function of those 2 features. But if you did a scatter plot, you would just have a grid of samples at the integer values. So that's not very useful. So what we're instead doing is we're making the size of the dots proportional to the number of samples that landed, that were 10 and 10 in this case. So, and then secondly, we're using the color of the dot to denote whether the samples were benign or malignant. Okay, so here what we see is if we focus on the benign samples, we see that they're mostly concentrated down here, and the malignant samples are pretty much spread out, but mostly, here's the biggest red dot. Okay, so making this plot took a little bit of effort. That's what's in this piece of code, but if you ever had to do this yourself, you could just copy and paste that code. Okay, so the main question for us, the main objective of what we're trying to do is, given this set of features, can we predict whether the patient is cancerous or not, whether the sample is benign or malignant. So that's the whole point of this unit. So in this case, we're just looking at 2, but more generally, in this data set, we have 9 different features. Okay, so that brings us to the problem we're studying, which is called binary classification. And so we can state the problem by saying, if we have a training data set of pairs where we have x vectors, these are feature vectors like we've seen until now, same as before. The difference now is that our targets, yi, are discrete. We could use any two integers or any two values to code them. It's really just a matter of notation. Like in that data set, we saw that they were 2 and 4. I don't know why, but for some reason they use 2 and 4. The most common ones that we'll use for derivation, just because it makes the derivations easier, are either going to be 1 or -1 or 0 and 1. And in this unit, we'll focus on 1 and -1, mostly because at least some of the derivations are a little bit easier that way. But you know, it's all the same. It's just two values, two categories really. You can code them however you want. And so you can imagine many, many applications of this problem. We saw one like, are these cells cancerous or not? Maybe we're given an image and we want to know, is this a weed or a crop? You know, possibilities are endless. But you could say what we want to do mathematically is we want to design some classifier that is a function of x that returns a value that is either 1 or -1 if that's our allowed label values. So that's at the end of the day what we want to do. So this function is a bit different than the one for regression, which returns a real number. In this case, we're returning one of two values from this finite set. And so when we say, like, what is the objective, we have to be a little careful. If you just say, like, I want that the prediction matches the truth, well, you know, even if you guess randomly, it probably will match the truth half the time. So matching the truth is really not so much the issue. The issue is, like, matching that truth most of the time or with high probability. So that's what we want to do. We want to match the truth with high probability. Maybe we won't be able to perfectly match the truth every single time, but we want to match it, you know, as often as we can. So that's our goal. And one way to think about this classifier, to visualize it, is in terms of the decision regions. So the decision regions would be the regions within the feature space. So for example, could be like x1 and x2 if you had two features. So they'd be the regions that give either a prediction of -1 or a prediction of 1. So let's say the region associated with the decision -1 is a set of x values that lead your classifier to output -1. So for example, in this case, this could be one of the decision regions, and then this would be the other one. This is just something made up. You can imagine many other shapes. In fact, you could have disconnected decision regions. Anything is really possible, depending on how you design your classifier. So here's one region, here's another region. But this is a really nice way to visualize it and just say, like, whenever my features end up here, I'm going to predict one value, and when they end up here, I'm going to predict the other value.
What if it's on the line?
Yeah, good question. So if it's on the line, in this case, we're going to have to make a decision. So I would say in practice, it's almost never exactly on the line with real data. So it's not really that much of an issue. When it is on the line, that's the place where or on the boundary, that's the place where you're least confident. So, you know, you could also like flip a coin, but what we're going to do in this class is we're just going to say when it's on that boundary, we'll arbitrarily assign it to one of the two classes and think that that's probably never really going to happen. Okay, good. Any other questions about binary classification as the main idea? Okay, great. So let's just focus now on a particular type of binary classification, which is the one we will be focusing on for a while, which is binary linear classification. So linear here is the key point. So we can think of binary linear classification as a two-step procedure. In the first step, we compute what's called the score or the discriminant. We'll call it z, and z is going to be an intercept term plus a set of weights times features. Okay, so if you step back and look at this looks exactly like linear regression. The only thing I've done here is I've changed the variables. Instead of using beta 0 through beta d, I'm now using b for the intercept and wj for the weights. And I'm doing this just to be more consistent with other literature out there on classification. You see this more often. But mathematically, it's no different than the beta 0 and beta 1 through d. Okay, so that's the first step, is you compute this z. But again, in classification, we must output something from our allowed label space, which is just going to be discrete. So as a second step, we're going to do some quantization. So we're going to say that y hat is going to be 1 if z is 0 or greater, or minus 1 if z is less than 0. And so here you can see I've more or less arbitrarily assigned the boundary value of z when z equals 0 to the class 1, but nothing would really change if we had set it to the class minus 1. Okay, so this is the procedure, two-step procedure. The things we need to learn from our data are the coefficients, the weights and bias, or weights and intercept, just as before. And that's going to be the challenging part. As we'll see, that's what we'll spend pretty much all of today on. And of course, once you know these parameters and someone gives you a new test sample x, you would just immediately compute the corresponding z, and then you would quantize it to get your target y hat, which would then be either the value 1 or minus 1. Okay, so that's the procedure we're going to be focusing on. So this is, when we say that it's a linear, it's actually linear in two different ways. On one hand, it's linear in the parameters we have to learn, at least the z is. And as we saw before, that's nice because that helps us. It makes our lives easier when we try to optimize these parameters. But it's also linear in the features themselves. And that is useful in terms of visualizing what's happening. In particular, when we go to plot the decision boundary, okay, what is the boundary? It's the point where we're right on the edge between 1 and minus 1. That would be the point when z is exactly equal to 0. And by definition, this is the value of z. So you might ask, well, what are the set of points x that make this true? Well, I think the easiest way to describe it is like this. It's the set of x such that this equation holds true. So that's what it is. And because that set of points, because this equation is linear in x, it means that this boundary will also be linear in x. So these here are just simple cases where you have two features, x1 and x2, in which case the boundary is a line. If we had three features, we would have this volume, and the boundary would be a plane, right? If you had four features, well, now we can't visualize it very well, but it's what we call a hyperplane, which is just a higher dimensional generalization of the plane. Okay, so even though it's hard for us to visualize, all of the intuitions that you get in 2 and 3 dimensions carry over directly, and you can trust them. It's no problem. Just visualize in 2 or 3 dimensions, and it tells you what happens in higher dimensions, at least up to any finite value. So this is what we have for the decision boundary. And the fact that it's linear helps us understand, when this is going to be a good method, when it's not going to be a good method. Because now we see that, for example, we cannot do something like this, at least directly with binary linear classification. However, as we'll see, we can, if we pre-process our features non-linearly, then we can do this with binary linear classification, but at least if we don't do any pre-processing of our features, then we have these hyperplanes. Okay, so the decision boundary here is linear in X. Okay, so linearity in the parameters, but also linearity in the features. All right, any questions on this? Okay, great. So now that we understand how this linear classifier is working, it's just basically cutting through the space of all features and trying to partition it into two half spaces. We can see that when our data is separable in that way, things will work great. And we can also imagine cases when our data is not separable where things won't work well. I'll show you some pictures in a moment. But when the data is separable in this way, we call it linearly separable. So that means that there exists some hyperplane, and again, the hyperplane, we'll think about it this way, some set of X such that this equation holds true. And of course, the location of the hyperplane will depend on our setting of B and W. But when this hyperplane separates the samples according to their class, meaning on one side of the hyperplane is all class yi equals 1, and the other side is all class y equals -1. In that case, we say that this data set is linearly separated. Okay, so here's a picture of a data set where we use squares for one value of y, circles for the other value of y. And you can see there's actually many planes or lines in this case, many ways I can split this. Right? So when you can split it one way, it's usually not unique. Usually there's many different ways you can split it perfectly. Okay, so that's what we mean by linearly separable. In practice, this is almost never something that happens, but maybe with the right pre-processing, maybe you can get it to almost happen. You can get it to be almost linearly separable, meaning there's just a few exceptions. And I would say that usually does happen, or at least happens when we're successful. But here's some pictures of non-linearly separable data sets. Okay, so this one is linearly separable, but for example, this one is not linearly separable because there's this one red point over here. So I would say that in this case, linear classification is still going to work pretty well. Okay, it made one mistake, but it's not so bad. Over here is a much more serious issue, right? There's really no way that I can make a linear partition of this two-dimensional space where I can cleanly separate the blue and the green. It's just impossible. So in that case, linear classification would work terribly. Here's another case where linear classification would really not work very well. Maybe you could try to do something like this, but still you're going to make a lot of mistakes when you do that. Okay. So you might say, well, why are we focusing on this method if it's not that great of a method where it's pretty limited? So there's several reasons. One reason, it's pretty easy to understand, especially relative to more complex methods that are nonlinear. Another reason is it facilitates feature selection. In other words, it tells us which features matter most. That can be really important in some scenarios. If we want to say, like, I have a whole bunch of features, but which ones actually matter, then by looking at the size of the weights, assuming our data is standardized, the bigger weights correspond to the more important features. So we can still do all the feature selection stuff that we talked about in the last unit. Okay, now we can also be a bit more clever. We can incorporate nonlinear feature transformations to change our data and then apply linear classification. And so, for example, if we did that, we could actually tackle this problem here. So one way to do a nonlinear transformation of this data is if you define the centers here and the radius, let's say this would be a fixed radius. What we could do is we could construct new features which are basically, the radius, call that x prime, and then just now we have a one feature instead of two, but now we have a very clean separation in that new feature. If it's, if the points are less than a certain radius versus greater than a radius, we can cleanly separate the data. So the nice thing is, if you do nonlinear feature transformations, then all of a sudden this method becomes more powerful. So the question then was, well, how do you know how to do the transformations? And that's a great question. But it turns out that that is something that we can learn. And we'll hold off on that for now. We'll focus on that once we get to neural networks. But in some sense, when you look at these really sophisticated methods that are used in practice, that are the state-of-the-art methods, what you'll notice is that at the end of a long set of processing steps is some linear classifier. And you could view all those other processing steps as just a fancy way to do these nonlinear transformations so that that linear classifier works well. So that's what happens in all these cases. And so it just shows you a little bit of why we're going to try to understand linear classification. Because even though it might sound like not a very good method, it's actually really powerful with the right pre-processing. And that's really the basis for all the machine learning that's done today. So it's a building block in these more sophisticated approaches. Yes.
What was the reason that nonlinear classification was bad then? It can't do these types of things? Is that the...
No, so with nonlinear classification, that's just the general case that you can do anything. And when it's linear classification, now your boundary has to be linear. So linear classification is a special case of all methods. It's either linear or nonlinear. So.
And then when you make it linear, that's when you get these extra features that it's just easier to understand.
Well, it's easier to understand, yeah. So we have a simple linear equation of our parameters and of our features. So it's just easier to understand, easy to derive things. So that's one reason to do it. And then there's these other reasons. It has feature selection is something that is actually quite difficult to do with a neural network. It's because now you're going to process all your features and make them unrecognizable, and now it's really hard to say which ones were most important. Whereas linear classification or linear regression, that just gives you that directly by looking at the weights. Okay, any other questions on this? Okay, oh, yes.
So you have you can solve everything using linear regression or linear classification. So why do you need nonlinear weights?
Oh yeah, so if your data is linearly separable, then this is all you need. But in practice, it's not usually so friendly.
So you can transform the nonlinear features to linear ones. So why do you need nonlinear classification?
So yeah, if I do some nonlinear transformation of my features, maybe I then think of that as part of my classification method. And so now that method is nonlinear. So it depends, when you say the classification is linear, nonlinear, are you talking about in the raw features? Or are you talking about in some pre-processed features? So like here, if I look in the raw features, I'm forced to make lines and I can't do well. But if I allow this pre-processing that's nonlinear, now I have essentially a new feature which is just measuring the radius. It's just thresholding any points that are inside or outside a circle. So it's sort of a matter of definition. Do I say that this method is linear in x prime, or do I say it's nonlinear in the raw features? Right? You could think about it either way. But in practice, we usually have to learn the transformation as well as the classification. So this knowing this is not something that usually happens, and so that's why more sophisticated methods are nonlinear. They're considered nonlinear because they have to do the learning of the transformations from the raw features in addition to the last step, which might be a linear classification in some transform features.
So we like we usually just use the nonlinear classification.
Well, the advanced methods will be nonlinear, but for now we're going to study the linear one just to understand it first. Okay, great. Okay. Any other questions? Okay. So let's make a naive attempt at the problem. The real problem for us is fitting these weights, B and W. And so, given that we've learned all about least squares linear regression, we could simply try to apply that to this problem directly. So in that case, we would say, well, I have some training targets. They happen to be 1s and -1s, but that's fine. I could still fit a model to y minus, let's see, how do I want to write it? A, and then my new parameters would be a vector with b on the top, and then w would be all the remaining coefficients here. Okay, so these are my parameters. I used to call them beta, but now I call them b and w. This is my A matrix, which has the column of 1s, and then all the other columns are the features. Here are my targets, which happen to be 1s and -1s. So this is certainly something that we could do, right? We know how to do it. And then the question is, well, does this work or does it fail? And if so, when and why does it fail? So to help answer this question, and by the way, so once you fit the parameters b and w, then let's say that these are the least squares values. Now to actually implement the classifier, it's that two-step procedure. We're first given a new test vector x, you compute the score z, which is a real number, but then you threshold that score to get your binary output y hat. Because for classification, we always need that binary output for binary classification. Okay, so this is just a simple experiment that I constructed when we have just a single feature. And so here's the data set. So there's 8 training samples. Okay, so here's x. And you can see the values of the training samples, the targets are always going to be 1 or -1, because that's what we have. And so, so to fit the least squares problem, this one, we know how to visualize this. We're looking for the line that minimizes the sum squared errors, right? We want to orient our line, tilt, and shift until the sum squared errors are minimized. And it turns out when you do this, you get that orange line. So really that's the line that parameterizes this first part of the two-step process. And then the second part is there's going to be a quantization. So that's where the green one comes from. So anytime that this line is positive, we're going to quantize it, or non-negative, we'll quantize it to 1. And anytime it's negative, we'll quantize it to -1. And so this green one is our final classifier prediction based on this method. And when we step back and look at this, it looks like everything worked really well. So our training data are these 8 points here, and the final prediction, classifier prediction, is the green line, which looks totally consistent with our training data. It looks like everything's great. So we might be initially satisfied and think, yeah, this works pretty well. So, but it turns out that it's pretty fragile. So if what you do is you take this last point and you just slide it over here, and you redo this least squares fitting process, now the problem is that your regression line, the one that's giving you that score variable z, because of this point here, that gets pulled to the right. And now when you quantize that, when you look at the positive values, they occur at this point. And in fact, this new classifier is not even going to get the training values correctly. It's going to make a mistake on that first training value. It's going to say that should be a -1. Okay, so something happened here that's not ideal. And the way I'm describing it here very heuristically is just in terms of whether the data set is balanced or imbalanced, but that's it's really just a special case to illustrate why least squares is not really going to be enough for us, why it's not the right loss function anymore. In fact, if you think about this edge sample that we moved here, from one perspective, this should actually be, these guys are the easiest samples to classify, because like if you're just looking for a way to partition into -1 and +1, as you get closer to this line, that's where it becomes difficult to make a decision, right? As you get farther from the line, it should be easier. So this is like the easiest point to classify, and somehow by making that large, I've thrown everything off. So something is really just not well designed here. And it happens to be this RSS minimization, this least square step, that's what's messing everything up. Okay. Any questions on this example? Okay, so let's do this again for our breast cancer data set. So we're going to extract these two parameters. We're going to repeat the same procedure. Of course, in this case, we need to plot the boundary. So the boundary, in this problem, the boundary was just, essentially was just this value, right? We're trying to figure out, should the boundary be here? Should it be here? Where should it be? Now, in this case, the boundary is an entire line in this two-dimensional space. So when we make that boundary, we're basically saying green on this side, red on the other side. But the question is, where should the boundary be placed? And so it turns out, in this case, if you go through the least squares fitting with the data, same as we said on the page above, you end up getting this boundary. And here again, you can see that it's doing fine on the red data, but okay, so it's misclassifying all these red points, which there's a lot of red and green on this side, so it's basically making a lot of mistakes over here. And just by eye, as a human, if you were forced to pick a boundary, you would probably, pick something more like this, right? Which has mostly green on this side, mostly red on the other side. So again, something is going wrong, and once again, it has to do with this RSS loss or least squares. And in fact, the problem heuristically is the same. It's this imbalanced idea where these are kind of concentrated here, the red is spread out, and it's not really handling that well. Same thing that happened over here. Okay. So is that making sense from the? Okay, so hopefully I've convinced you that RSS is not the way to go. Let me just make one other small point here. In case it's a little bit confusing as to what's happening with this boundary, let's just make it more explicit. So what we said here is this is like the set of x such that this equation holds true. So in this two-dimensional case, we can be a little bit more precise. So in this case, x transpose w would be, the x vector is just x1, x2. The w vector is w1, w2. So when we do this, this vector-vector multiply or inner product, whatever you want to call it, this gives us x1, w1 plus x2, w2. Okay, so that's what this term is here. And now if you just isolate the x2 variable, we can get more explicitly an equation for that line that you can easily plot. So you end up getting minus b over w2 minus w1 over w2 times x1. Okay, so if you wanted to plot this boundary, you would use this equation. This is the equation of x2 versus x1 on the boundary. Okay, just trying to make this a little bit more concrete. Okay, all right, so that's all I wanted to say here. Any questions on this? Okay, so now let's get into the meat of it. So the approach we're going to describe is known as binary logistic regression. It might sound strange that we're using the term regression when we're talking about classification, but the fact that regression is the traditional term here reflects the fact that part of our two-step process really looks like a linear regression. So that's kind of the origin for why this term regression is used for a classification method. Okay, so that's, just to remember, what we're doing is linear classification. We're doing this two-step process, computing the score, and then we're quantizing the score, or thresholding it. So the question that we're trying to answer now is, how do we design these parameters? We saw minimizing RSS is not a good way to go. So we need to come up with a better way. So what we're going to do is we're going to exploit some of the random variable stuff we talked about more recently, and we're going to think of coming up with a probabilistic model. So it's going to be like this. The probability that y equals 1 given the score is going to be some equation, some function of that score, and the probability that y is minus 1 given the score is going to be some other function. Let me show you a plot. This is sort of what we want over here. Something that looks like this. So here's the score, and here's the probability that y is 1 given that score. So you can see that as the score gets more and more positive, the probability that y equals 1 increases. As the score gets more and more negative, the probability of y equals 1 shrinks to 0. Right? So this is like 0 here, 1 here. And right in the middle, right on the boundary when z equals 0, we're going to say the probability is 0.5. It's like we have no idea. It's equally likely, or equally probable that that's going to be that y is a 1 or a minus 1. Okay. So basically, any kind of function that has this generic shape, there's many of them that people use, or that you could use. It just shows you that there's, as z gets more and more bigger and bigger, you have more confidence that y is 1, and as z gets more negative, more confidence that y is not equal to 1, essentially. So that's the main idea. So among all the different functions we could make here, the one that's the most tractable looks like this. So ez, e to the power z, over 1 plus e to the power z. And then the other one is 1 over 1 plus e to the power z. Okay. So why are we doing this? Well, anytime you have things like e to the power z, those are super easy to differentiate, because like if you differentiate e to the power z with respect to z, you get e to the power z. So it's very friendly for computations. Another thing that we need out of this pair is that we know, based on the law of total probability, that if you fix z, the probability of either this or this occurring has to be 1, right? You have to be able to sum these together to get 1. So you can see that this is true. If I sum this and this, then no matter what z is, I get 1. Okay, so that basically, that's what we require for this valid conditional probability mass function, and that happens. Okay, so this is basically like just a really simple, analytically simple function that works for us in this way. There's definitely other choices. This is not optimal in any sense. It's just very convenient, and it's sort of the workhorse function that most people use. It's called, this function we've built is called the logistic function, or the sigmoid. And by the way, this thing can be simplified. We can multiply the top and bottom by e to the minus z, and if we do that, then we can write it as 1 plus e to the minus z. Right, so those are equivalent, and this one here is a little simpler because z shows up only in one place rather than in two. So this is often what we'll use to describe this function here. Okay, all right. So that's how we're going to go. Now that we have this probabilistic model, we essentially can use our maximum likelihood framework, and we'll get to that in just a little bit. Okay, any questions on the model? Okay, so let's try to understand it a little bit before we move on. So the model on the previous page was written in terms of the probability of the label or the target given the score. But the score is like this intermediate quantity. The score is not directly, I mean, it's not exactly the same as the targets. Sorry, the features X, right? So you might say, well, that's fine. We know how to interpret that. But how do I interpret probability of y equals 1 given the features? Can we interpret that? So to do that, let's take the simplest possible case, single scalar feature x, and we'll even set the intercept to 0. So if we do this, what's the equation for z? What's the equation here? In the case we have a single scalar feature and intercept b equals 0. Just wx, exactly. Okay, so now we can maybe figure out what's going on. So we plug this z into this logistic model, this sigmoid, and let's try to understand the effect of w. So the first thing is here, and here's some pictures. So this is w equals 1 is exactly the 1 from the previous page. Now, if I change the sign on w, -1, what we actually do is we flip the direction of the sigmoid. Okay, so that can be useful. So that's what you get from changing the sign on w. Now, if we change the size of w, let's say we make w bigger, like 10, what happens is this sigmoid now becomes very steep, very sharp transition. On the other hand, if you make w smaller than 1, now the sigmoid becomes wider. It's the more less sharp transition. So essentially, that is how w affects things. For each of the features, you can imagine changing the sign, changes the direction of the sigmoid, and changing the magnitude will change how quickly the model responds to that feature. Is that making sense? Effective w? Okay. Now we can bring, and all along, in all these cases, when the bias or intercept is 0, then the transition is always happening at x equals 0. Okay, so when we bring in the b term, so we can, so first of all, since we're dealing with the scalar case, we have wx plus b. But to understand this a little bit easier, let's write it as w times the quantity. Actually, let's see, what do I want to do? Yeah. W times quantity, b over w plus x. Okay, so now writing it this way helps to understand the direct effect of w on x. So essentially what happens is the pictures look the same, but instead of transitioning in x equals 0, they transition when x is minus b over w. Because when x is this value, then this becomes 0. Okay, so as you change b, then you also have to know the value of w, but that will shift this sigmoid to the right or the left. So that's really the effect of b and w is they compress or expand and shift and possibly flip that sigmoidal shape. Okay. All right. Any questions? This? Okay. Great. So now we can be a little bit more technical, and we can finally get to this problem of fitting the model parameters. So we developed, at the end of the last unit, we developed this nice approach that is very general, and you can use it whenever you have a probabilistic model of this form, or a likelihood of this form, some probability density of the labels given the features and the parameters. In this case, our parameters are the b and the w vector. And as before, y is going to be a vector of our training targets. These will happen to be 1 and -1 in this case. And x will be a matrix. Each of these is a different row of x, and they're just the features for each training sample. And if you remember, the way maximum likelihood works is you just find the values of the parameters that maximize this likelihood. That's essentially all it is. When you do the derivations, it's often more convenient to work on minimizing the negative log likelihood. It's equivalent, but it's a little bit easier. So let's just review. The last time we saw this, we applied it to linear regression. So in that case, the likelihood took the form of this Gaussian distribution where we have a mean of A times beta. We had a variance. This is a multivariate Gaussian, so we have a variance of sigma squared times the identity matrix. And when you look at the negative log of this likelihood, you end up getting a quadratic plus a constant that does not depend on beta. And finally, if you want to minimize this with respect to beta, you can ignore this part. You can just minimize this. And that is exactly minimizing RSS, or least squares fitting. Just a quick review of what we saw at the end of the last unit. So we're going to use exactly the same procedure. The only thing different will be this part. Now we don't have this Gaussian noise-based likelihood. We have this logistic likelihood here. That's the only difference. But the procedure is the same. Okay, so we'll go through the details in just a moment, but are there any questions on the big picture? Okay, let's see how we do this then. So there's a little derivation. You'll see it's not really very bad. The tricky thing about this likelihood that we have now is that there's no single way to write it. There's really two cases to consider. There's the case when the targets equal 1, and there's the case when the targets equal -1. So when I talk about the probability of some event happening, that's when I use this capital PR. This is like the probability of the event yi equals 1, given this stuff. On the other hand, when we talk about PMFs or PDFs, then I use the small p. So that's just to try to explain what the difference is here. But essentially, that's the main difficulty in this derivation, is figuring out how to deal with the fact that this likelihood, there's really two different forms of it with two different equations to deal with. But I'll show you. There's a simple trick that we can use to get around this. Okay, so we start with our likelihood. We need to write this in a convenient form, but at least that's the thing we're working with. So the first step in all these cases is to use our independence assumption, which is to say that all of these target values, all our training values yi, they're all independent of each other if you condition on the parameters and the features. So that allows us to write this joint probability as a product of scalar, or what they call marginal probabilities. Okay. These guys are things we can work with. Now, as we said before, typically we like to work with the negative log rather than the raw likelihood. So in this case, when you take the negative log of this product, you end up getting the negative sum of the log of those terms. So taking that log turns this product into a sum, which is very convenient. That's basically from this idea. And now we're ready to figure out how can we write these terms in terms of these things here. So there's a trick to do it. I think about it as a switching variable. So if I create this term here, remembering that yi is either 1 or -1, this can take one of two values. When yi equals 1, this term becomes 1. When yi equals -1, this term becomes 0. So this thing basically acts to turn on or off a given term. So when I put that here in front of this term, that means that this term comes alive for all the samples I for which yi equals 1. This turns into a 1, and this term comes alive. On the other hand, here I have 1 minus that term, which goes to a 0. So that means this is gone anytime you have an I when y equals 1. Okay, so that's how I'm turning this into the proper value of these two when y equals 1. Now, when y equals minus 1, then this goes to 0, this goes to 1, and then you get this. Okay, so that's essentially how we're turning this into either this or this, depending on the value of yi. So that's the hardest part. Is this making sense? Any questions on this? Okay, if you understand this, then everything else is easy. Essentially now we just have to take the log of those two terms. So let's look at the first one. When you take the log of this, you get log of the numerator minus log of the denominator. Okay, so log of the numerator is just simply z. That's what this is. Minus log of the denominator is this. Can't really simplify it at all. On the other hand, over here, take log of this, you get log of 1, which is 0, minus log of the denominator, which is again this. And now you just have to multiply these terms out. When you multiply them out, you get these 4 terms. And it turns out that 2 of them cancel. And so you end up just with the remaining 2 terms. And this is the equation for the negative log likelihood. Okay. So it's written, in a slightly convoluted way where this part is written in terms of the z's, and then the z's are a function of the b's and the w's over here. This is a pretty common thing that shows up in machine learning where you have one part in terms of some scalar variables and another part which those scalar variables are written in terms of the parameters of your model. Okay, but this is essentially the most we can simplify it down to. So now we have a negative log likelihood. Now to actually solve the problem, we just need to figure out how to set b and w so that we minimize this. Unfortunately, there's no analytic way to do this, like with least squares, where we can just write down an equation. Is something you need to implement with an algorithm. But it is one of these convex. This is convex. It can be done. Scikit-learn does it for you. So I'll show you those details in a moment. But this is essentially it. This is the negative log likelihood derived in simplest form. And this is the thing we minimize by choosing b and w, given our training data. Any questions on this part? Okay, great. Let's go back to our example, the one-dimensional example where we saw previously that when we used least squares linear regression, it fell apart. This somehow distracted the whole model. Now, when we do this with logistic regression, there's no problem. So this is the equation for z, which needs to be aligned because that's linear regression. And we can see that it's transitioning at a very nice place, which is just where we would expect. And in this case, we can also plot the probability assumed by our model. This is the probability of y, probability that y equals 1 given x. And you can see when x is to the left of here, the probability is less than 1/2. As you go farther to the left, the probability shrinks towards 0. If you go far to the right, the probability increases towards 1. And so like for this point, you're very, very confident that the target value is 1. Probability of that happening is very close to 1. Of course, if you're right in the middle here, right on this threshold, the probability is 0.5. You just really don't know whether it's 1 or minus 1. Okay, so this just applying it to that simple example and confirming that yes, this does solve the problem we saw before. And we're almost done. So this is just a summary slide. This is what we derived before in just 2 slides ago in the case that the targets are 1 and minus 1. That's one of the ways that this shows up. Another very popular way that this equation is written is when the targets are 0 and 1. In this case, this switching variable, it just reverts to yi because that's all you need. So in this case, has a slightly different form. So when you write this down, you just have to know, how are your targets defined, and you can write down the correct version of the model. So this is known, sometimes it's known as the logistic loss. More commonly, this is known as the binary cross entropy loss. So to explain that, there's an explanation using a term from information theory called the entropy. There's another way we can write this. Maybe I'll assign it as a homework problem. It's not super important, but it helps to explain where this name comes from. Okay, so just one last thing to talk about very quickly is that when we use this in practice, we typically want to add a regularization that looks like ridge regularization. And in fact, in scikit-learn, this is added by default. And there's a reason to do this, which is that if you don't do this, something really bad happens when your data is perfectly linearly separable. Turns out, if you look at this closely, you can deduce that when your data is perfectly linearly separable, the way to minimize this is to make your parameters W and B as large as possible, like make them infinity. And so this algorithm will just try to make them bigger and bigger and bigger and bigger the longer you let it run. And this is something you don't want to happen. So by adding this term, it just prevents that from ever happening. When you do that, typically you choose a very small value for alpha 2, just a small number, and that will keep all your weights finite. Of course, we also know that this can help with correlated features, and it helps here just like it did with linear regression. So that's another use for this term. In that case, you want to use a larger value of alpha 2 and tune it using cross-validation, just as we did before. Now, there are other options. We could also use L1 regularization here, and just like we saw before, if you do this, you will get a subset of weights going exactly to 0, doing feature selection, and so we can do that for classification too. We can do feature selection just as before. One final comment, though, is numerically the optimization algorithms that you need for these two cases are a bit different, because in this case, this is a differentiable function of W, whereas in this case, it's not differentiable. You have to use another family of algorithms. These algorithms are slower. They take longer to give you the solution. So depending on how big your data set is, that means you might have to wait longer to solve this. Just things get more expensive, and as you play with these things, you'll see what I mean in sklearn. So that's it for today. Next time, I'll briefly talk about how you implement this in sklearn, and then we'll move on to the case where what if you have more than 2 classes? We'll talk about that on Friday. See you guys then.